From our definition of the Gibbs free energy, we can now write our change in Gibbs free energy at the standard state of the reaction in terms of the change in enthalpy of the reaction, or the standard state heat of the reaction, and the standard state entropy change of the reaction. Just a reminder, this delta G here refers to the expression where I summed over all the components stoichiometric number multiplied by the Gibbs free energy of the pure component at standard state. Exactly the same for delta H in this case and delta S in this case. So it does not refer to an end minus a beginning or an in minus an out. Furthermore, it refers to the standard state at a specific temperature, which implies that we have a constant temperature when we are evaluating this equation. So if you want to say that, but what happened to this part of our expansion, it is equal to 0 because the temperature is constant at the standard state. In this course, in order to determine the temperature dependence of K, we are going to make this simplifying assumption that the standard state heat of reaction and the standard state reaction enthalpy is relatively constant with temperature. Over short temperature intervals, that is a very valid assumption. With that in mind, we can divide both the left-hand side and right-hand side of that expression by RT. And then we want to see how does delta G over RT change with temperature. So we take the differential to temperature of the right-hand side of this equation. And with our assumption of constant delta S and delta H, this is the resultant expression. Recall that ln of the equilibrium constant is equal to minus delta G over RT. We can now substitute this expression instead of this group of terms into our differential equation. And now we can integrate between boundaries ln K at temperature 1, ln K at temperature 2, and temperature 1 and temperature 2. After integration, we get our beloved Van Hoff equation that gives us the relationship between equilibrium constants determined at different temperatures, standard state values, as a function of the heat of reaction under standard state conditions, which we assume to be independent of temperature when we derive this equation. So we can now calculate or determine our equilibrium constant at 298, for which we can find information on the standard state in tables. That will then be our temperature 1. And then we can calculate our equilibrium constant at whatever temperature we are interested in. The bigger the difference between temperature 2 and temperature 1, the less accurate this linear interpolation or the assumption that delta H standard state and delta S standard state is independent of temperature becomes, and we have to get rid of that assumption. We are not going to do that derivation in this course. You can see Smith, Van Ness and Abbott for details. Just be aware of the fact that we are making assumptions and that it may influence the accuracy of our answers. This slide gives a summary of all the equations that you will find on your data sheet. Please note that these two equations, the equilibrium constant and its temperature dependence, only depend on thermodynamic parameters of the individual components and the stoichiometry of the reaction. The composition-dependent group of terms can be calculated at any point during the reaction or when we mix the reactants before the reaction actually starts. It is only when we reach equilibrium that this group of terms will then be equal to our equilibrium constant that we determined from thermodynamics. And we can in fact use a comparison between whatever is currently present in our mixture and the equilibrium constant in order to determine whether the reaction will proceed in the forward or in the reverse direction as written.